Why does a racing car generate heat when it runs on the track? Why does a mousetrap car, after traveling a few meters, not keep moving forever but eventually stop? The answer to this question lies in the concept of friction. Friction is one of the main enemies of anyone building racing cars. Reducing it means reducing energy losses. However, once understood, friction can also become a very useful tool in the hands of the designer. A major difference between racing cars and mousetrap cars in the type of propulsion. Racing cars are continuously powered by an engine and can therefore over very long distances. A mousetrap car, on the other hand, moves thanks to the elastic potential energy stored in the mousetrap spring. When this energy is exhausted, the car slows down and eventually stops. When the spring is released, part of the elastic potential energy is transformed into kinetic energy, which sets the car in motion. Another part of the energy is dissipated as heat due to friction. This means that if dissipative friction is too high, the mousetrap car will lose too much energy and may stop before completing the race. But which parts of the car generate friction? The main sources are the contact between the wheels and the floor, the contact between the wheels axis and the chassis. Air also generates friction called aerodynamic drag, but since the mousetrap car is very small and moves at relatively low speed, this effect can be considered negligibly. Let's analyze the friction between the wheels and the floor. This type of friction, called static friction, is essential for the car to push against the ground without slipping. If it is too low, the wheels would spin and the car would remain in place, just like on an icy surface. This friction is therefore useful, as it allows to to become the spring's energy to be converted into motion. The friction force can be expressed by the formula where m is the coefficient of friction between the wheels and the ground, and n is the normal force, which corresponds to the weight of the car. It is therefore important to carefully choose both the wheel material and the overall weight of the vehicle. Materials that are too heavy or dense increase energy losses, while materials that are too light may reduce stability or grip on the ground. Wood has traditionally been used because it is relatively light, but it can be difficult to work with precision. A car that is not perfectly symmetrical may wobble and leave the track. For this reason, a very effective solution can be 3D printing, which allows very precise structures to be made using materials such as PLA, a good compromise between weight, strength, and precision. Another major source of energy loss is the friction between the wheel axles and the chassis, known as dynamic or dissipative friction. This type of friction represents lost energy and should be minimized as much as possible. An effective solution is the use of ball bearings, which significantly reduce friction. Some bearings, such as ceramic ones, can almost completely minimize this energy loss.
Once we understand how friction and energy dissipation work in a mousetrap car, they can become powerful tools that can be used differently depending on the competition category, in particular in the acceleration and regularity events. In the acceleration event, the objective is to travel 5 meters in the shortest possible time. Therefore, sources of energy loss, such as friction in the axles and other dissipative effects, should be minimized as much as possible. For this reason, it can be advantageous to reduce the number of wheels. Using 3 wheels can be a good compromise because it reduces friction while still maintaining sufficient stability. However, using fewer wheels could make the car unstable. It is also important not to make the car excessively light, because when the spring is released, the vehicle might jump. This effect, together with vibration of the structure, can cause a significant loss of energy. For this reason, it is essential that the car has a very stable structure. The length of the lever connecting the spring to the string that turns the wheels is also very important. The shorter the lever, the faster the stored elastic energy of the spring is released. This means that the initial acceleration will be very high, but the distance traveled will be shorter. This is important because the goal of the acceleration event is precisely to travel a short distance in the shortest possible time. The ideal car is therefore one that stops shortly after the 5 meters mark. If the car continues moving well beyond the finish line, it means that part of the available energy was not used efficiently to increase the speed within the required distance. In the regularity event, friction plays a different role. The objective is to make the car travel 10 meters in exactly 7 seconds. The lever must therefore be longer than the one used in the acceleration event, since the distance to be covered is greater. The goal is no longer simply to minimize friction, but rather to regulate the overall behavior of the system so that the car moves at the desired speed. The friction between the wheel axle and the chassis cannot easily be changed once the car has been built. Therefore, if many tests are required, it can be useful to adjust other parameters of the systems, such as the total mass of the mousetrap car. The mass of the vehicle can easily be modified by adding a small container to the structure that can be filled with different materials. By adding or removing material, the overall mass of the car can be increased or decreased, allowing the motion of the car to be fine-tuned during the testing. In this lesson, we learned that friction is a fundamental factor when building a racing mousetrap car and cannot be neglected. To make the most of the available energy, it is essential to fully understand how the system works. These principles allow mousetrap cars to be optimized for the different categories of the Monaco Mousetrap Grand Prix.